Hi, my name is Joaquin Salas, and I would like to thank LatinX for this invitation. In the photograph that I'm displaying, I'm showing you a storm that hit my hometown, Querétaro in Mexico. And it happened a couple of weeks ago, but soon afterwards, we realized that it was one of the strongest hitting the city in over 20 years. As we start convincing ourselves that these events will happen more often, we need to think about how we should change to face the challenges ahead of us. You see, well, in this context of extreme events, preventing is no longer an option. The last IPCC report confirms two things, without a doubt. One is climate change is caused by human activity. And two, that nothing is preventing the planet from increasing its temperature by 1.5 degrees Celsius, not even if we stop emitting CO2 like right now. Thus, we have to devise ways to mitigate and adapt for climate change, and also see if we can ameliorate the effects of biodiversity loss and maybe avoid them. And we need to devise ways in which artificial intelligence can help us. This graph shows you the measurement of CO2 in a place of paramount importance, the Mauna Loa Laboratory in Hawaii. It has been said that it is safest to stay below 350 particles per million to avoid the so-called tipping points, or the points that beyond which the system, the climate system, becomes unstable and cannot return to this state that we live in. However, by September 2021, the average measurement was 416 particles per million. To put this into perspective, scientists have shown that we haven't seen these levels of CO2 in the atmosphere in the last 3 million years. So, on the other hand, we have computing powers on the rise. Here I'm showing you the performance of the top 500 computers in the world. The fastest computer currently delivers about 442 petaflops, and there are plans to unveil first single systems providing at least 1 exaflop later on this year. So we have climate change on the one hand and powerful supercomputers on the other. Now we may ask ourselves, since we are interested on this topic of machine learning and artificial intelligence, is there a way to leverage on the intense activity around artificial intelligence? So climate change and loss of biodiversity are two of the most critical existential threats that we are facing in our generation. And well, we can say that at least for climate change, we have a strategy. May not be very good, but we have one. So we need to go net zero by 2050. However, there are no technological fixes for species that goes extinct. Simply put, there is no economically viable solution. Now, I'm going to share with you some of my experience implementing computer vision and pattern recognition solutions aiming to tackle climate change, avoiding biodiversity loss, and in general to preserve sustainability. So let's start with bumblebees. Between 2006 and 2011, there was this phenomenon called colony collapse disorder. At that time, millions of bees were dying, and no one knew why. Even now, I would like to invite you to look at your car defense after a trip. You will notice that there are very few insects. So several years ago, we started studying bumblebees and their dynamics. For instance, here in this slide, I'm showing you how we created computer vision systems to detect and track both bumblebees and flowers. The purpose was to determine when bumblebees arrived and how long they were staying. Then we constructed systems to assess the health of the bumblebees. Using high-speed cameras, we measured their flapping frequency using the analysis of their wings' optical flow. Using these tools, we could determine how many bumblebees were, for instance, leaving or entering the beehive, and also follow their trajectories using these methods. Now, on a different topic, one related to preservation of biodiversity, we were interested in identifying individual animals. For instance, we wanted to take apart jaguar Joselito from jaguar Toñito. Sometimes people use neck laces with GPSs, but we wanted a non-invasive solution. We developed a strategy that used generic features, such as the one you may extract with a SIFT to detect individual animals. Then we employed users' feedback to improve our inference mechanism. This approach resulted in a semi-automatic framework where actually humans were in the loop and they were collaborating with the inference system. We worked with geckos, otagoes, wild sharks, and salamanders. In our pipeline, we uploaded an image into the system, and then pre-processing consisted on things like segmentation, illumination correction, or specularity removal. As I say, we extracted generic features, and these included SIFT, SURF, orb, local histograms, or affine invariants. Then, using these features, we retrieve candidates. At that point, user relevance feedback helped us to replace the priors with the posteriors for inference. The system is an example of how biologists, computer vision researchers, and citizen scientists could collaborate in conservation efforts. Now, it has been said by 2050, the world will need to increase its food production by 50%. This is a big challenge. However, the soil is already being subject to much stress. Our purpose was to develop a system to monitor the soil, verify its state, and perhaps quantify the effect of management strategies. So we had a drone equipped with thermal and multispectral cameras flying around a fallow plot field. And then using additional atmospheric data and sensors buried in the ground, what we did was to perform a characterization based on the soil temperature changes through the day. Then we employed unsupervised strategies to segment the soil surface. In this characterization, we flew every hour from dawn to dusk, measuring the soil surface temperature in this fallow plot. The drone was equipped with thermal and multispectral cameras. Afterward, we waited for the plants to grow and then employed the multispectral cameras to predict the terrain segments. Thus, this procedure allowed us to map plant growth and the segments resulting from the temperature characterization. We think that this procedure could be used to monitor soil treatments and eventually assess the capacity of the crop plot to produce plants. Now let's talk about the forest. And this is essential because forests are the most important carbon sink in the land ecosystem. We have to take two crucial steps. On the one hand, we need to stop emitting CO2. And on the other, we need to remove CO2 from the atmosphere. And here, forest carbon quantification could represent a very important step that will allow us to reward owners who keep their trees healthy. Traditionally, we need to obtain structural measurements of trees, such as height, the diameter at breast height, and the crown diameter. Then, we use allometric equations to infer the amount of carbon content. In our strategy, we flew again drones over forest fields, while in parallel, we developed deep learning strategies to detect trees, and then computer vision techniques to obtain point clouds from where we could obtain the tree heights. Thus, the combination of tree detection and 3D structure allowed us to apply allometric equations to estimate carbon content on a set of trees. Let's keep talking about forest characterization. See, Mexico belongs to the 17 megadiverse countries in the world. It is a cradle of between 10 and 12% of the biodiversity of the planet. However, among these 70 megadiverse countries, it is second in deforestation, just behind Brazil. In this slide, I'm showing you a strategy to assess the state of a protected natural area. For learning, we use plots that we know are in regeneration. Then we construct an autoencoder to learn how to reconstruct these patches. Using the reconstruction error, we devise a classification scheme that distinguishes between regenerated and degraded plots. We construct 4 of these autoencoders, one for each of the seasons: spring, winter, fall, summer. Then using the autoencoder as an inference machine, we evaluated the whole natural protected area using satellite images. Then we classify the land between degraded and regenerated. This classification provided us with a tool to figure it out, the proportion of the natural protected area in the state of degradation or regeneration. Here, satellite images could be used to analyze historical records. For this protected natural area, we analyzed the evolution of the normalized vegetation index between 1996 and 2021. It is possible to observe that the healthier portion of the protected natural area is increasing its proportion with respect to the whole through this period. Now, satellite images could also be employed to assess vulnerability. In this slide, I'm showing you how we map satellite images to census information. We constructed this mapping between the satellite images and the census using convolutional neural networks. So instead of performing costly interviews and surveys, we were able to assess vulnerability at the residential block level and for the whole country of Mexico, and a cost that is neglectable compared with traditional efforts. The information contained in the census, in our case, corresponded to the proportion of houses in a residential block with running water, with sewage, with concrete floor, equipped with toilets, electricity, and how many occupants there were per bedroom. To solve the mapping, as I say, we use this strategy of deep learning known as convolutional neural networks. Employing the system, we assessed vulnerability at an increasing level of resolution, from the countrywide to the residential block level. Eventually, what we wanted was to determine vulnerability and help improve public policy making. Hopefully, or hope is that this will ultimately result in a more efficient distribution of resources. So what I have been trying to convince you during this talk is that machine learning can impact the way we address a series of challenging problems, such as climate change, biodiversity preservation, and vulnerability. Within this context, machine learning really provides us with a set of powerful tools that can be applied to a wide variety of problems. Nonetheless, power consumption of data-driven techniques can become an obstacle, especially if we want to apply this technology widely for an ample spectrum of problems. It has been observed that the way we use it now, our current strategies for learning, are producing diminishing results, diminishing returns, as more computing power is required to achieve small gains in performance. So, climate change and biodiversity loss are the challenges of our time. And we think that machine learning, as powerful as it is, can be very helpful. However, we need to choose well on how and when to use it to avoid detrimental consequences. Thank you very much for your attention to this talk, and I would like to take this moment to express my gratitude to all the collaborators that have made it possible to produce the results that I showed you during this presentation. Thank you very much.
So we'll start with the Q&A session for Joaquin Salas, and I'll start asking some questions, and feel free to ask them on the chat. But actually, I have a question before we start checking some on the chat, and I'd like to ask you, how big do you think that it will be the influence and importance of the industry as per se, companies such as Google, Facebook, etc., or maybe DeepMind, that is currently working on climate models and stuff, in the expansion and awareness of the usage of AI for the study of climate change?
They are big players all around. Their influence is very large and wide. Even for the information that they manage, by the impact of their applications. So the more they get involved in initiatives that take care of the planet, the more we think that will influence the world, and also it will create an example about what others could do. So these big players that are now among us will play a large role in the outcome that we will see.
I have a question. So I'm wondering about, most of the computing power and like modeling comes from generally very well developed countries. Yet a lot of the challenges that are coming from climate change also are coming from maybe countries that are developing at the moment, let's say something like places like India or Latin America. Do you see a problem there that maybe countries like US are sort of just blinded to how to study problems of deforestation in Mexico, for instance, just because we don't even know. Like,
your question is most important, Andres. So one thing that we are perceiving is that, yeah, that it is correct. Like in some of the most advanced countries, they perceive that some of the big incognites that they have about climate change, loss of biodiversity, in less well-developed countries, such as Latin America. So basically, they feel that they don't know what is going on. And so we need to raise awareness within our countries to advance in the development of models that are especially tailored to our needs. So, for instance, right at this moment, we have been approved a special issue on IEEE Latin American transactions to talk about what solutions have been developed in Latin American countries to deal with the problems that we are facing. And that is interesting in several directions. So we may expose what is being done, what are the better practices, and also we will let other people around the world know about what is the situation that occurs in Latin America. So yeah, you are right. I think it's a niche or an opportunity to raise awareness about what is happening in Latin America and to help construct a more robust community in the area.
Thanks, Joaquin.
Thanks to you.
I do have a question in the sense of how do you leverage or make do not make the chicken and an egg issue of to have more computing to actually analyze images, you have to have more carbon dioxide. How do you try to, is there any initiatives to try to manage this, to make sure that the computer is not generating more carbon dioxide?
We're not killing the patient while trying to heal him or heal her. I think that you're touching a very important topic. Machine learning methods at some point become very expensive. So that's a big issue because when we try to gain a few percentage of performance, we may be constructing more and more elaborated models that require more and more computing power. So that's a big issue. So I think that we need to address that in terms of the current situation, no? So do we really need these huge data sets? That may be something interesting to develop methods to previous to the learning process, learn to select what data is important. And also, maybe at some point we need to start shifting the paradigm with respect to the current technology. And so current methods are too much computing intensive. They demand too much resources. And we have evidence that in any case, not precisely how we learn. So there is also a lot of space to improve the capability of the methods to learn. So there are many areas of opportunity where we could address the issue of how much resources are we consuming in the process of learning to solve other problems, such that artificial intelligence becomes really a tool for solving and addressing these issues.
I would like to thank Joaquin for the amazing talk and everyone for the questions. And we'll cut to break and we'll see you in the next session. Thank you, everyone.